Microporous crystalline adsorbents, such as MOFs and zeolites, have a wide variety of pore dimensions, pore connectivities, and pore topologies. For example, AFI zeolite has one-dimensional channels whose width ranges from 7.3 angstrom to 8.4 angstrom. MAF X8 is a MOF with one-dimensional channels of 10 angstrom. Fe2 BDP3 has triangular shaped channels. Modernite zeolite has one-dimensional channels of 7 angstrom in size. These are connected to side pockets that can accommodate molecules such as methane and carbon dioxide. These side pockets are acting as cul-de-sacs. Sodium X zeolite has cage diameters of approximately 11 angstrom separated by 7.4 angstrom windows. Chabazite zeolite has cages of 8.5 angstrom in size separated by 3.8 angstrom windows. LTA5A zeolite has 11 angstrom cages separated by narrow windows of about 4.3 angstrom. MFI zeolite consists of a set of intersecting channels, straight channels and zigzag channels, and the channel dimensions are approximately 5.5 angstrom. In this presentation, I will focus on 1D channel topologies of zeolites and MOFs. Let's start with AFI zeolite that consists of channels of approximately 7.3 angstrom in size. If you look at the channel topology from the side, we note that the pores have a corrugated shape. Let's have a look at how carbon dioxide and methane traverse along the 1D channels. We note that the carbon dioxide that is most strongly adsorbed prevents the mobility or reduces the mobility of methane, and such slowing down effects are important for mixture permeation across AFI membranes or AFI zeolites. If we look at how benzene moves inside AFI zeolite, we note that the benzene molecules experiences a somersault. We look at how carbon dioxide and hydrogen move inside ton of zeolite. We see that the mobility of hydrogen is significantly higher than that of carbon dioxide, but carbon dioxide is most strongly adsorbed and serves to slow down the mobility of hydrogen by acting like goalkeepers in a football match. Let's look at how xylene isomers locate within the one-dimensional channels of AFI zeolite. Orthoxylene has a dimension that is 8.8 angstrom in this direction and 7.4 angstrom in width, and orthoxylene can locate very nicely within the grooves of AFI zeolite. And the packing of the orthoxylene molecules is face-to-face, that is optimal. Whereas the metaxylene and paraxylene have dimensions of 8.9 angstrom in this direction and 9.3 angstrom in this direction. This is too large to locate face-to-face with an AFI zeolite, and therefore the packing is less efficient. If we examine the unary isotherms of orthoxylene, metaxylene and paraxylene, we note that the orthoxylene has the highest absorption capacity due to the face-to-face packing. The cross-sectional shapes of metal organic frameworks are much more varied than in zeolites. For example, MIL-47 has 8.5 angstrom sized lozenge-shaped channels, and if we look at the motion of carbon dioxide and methane within the channels, we observe again that the most strongly absorbed CO2 has a important effect called the slowing down effect, and this reduces the mobility of methane within the channels. Benzene within the MIL-47 experiences a somersault as it traverses along the channel. The 8.5 angstrom sized lozenge-shaped channels of MIL-47 allow commensurate stacking of orthoxylene within the one-dimensional channels, and this results in a higher absorption capacity and strength for orthoxylene as compared to metaxylene and paraxylene. The orthoselective separations of xylene isomers can be accomplished with MIL-47 as demonstrated in these papers. Magnesium MOF 74 has hexagonal shaped channels of 11 angstrom. The unsaturated magnesium atoms are located along the vertices of these hexagonal channels. And if we look at the motion of hydrogen, we see that hydrogen being poorly absorbed rebounds on striking the channel walls. Carbon dioxide, on the other hand, gets attached to the unsaturated metal atoms and have a higher concentration along the walls than in the central core region. One of the oxygen atoms of magnesium, of CO2, attaches to the magnesium atoms, and on detachment, the motion of carbon dioxide follows a boomerang trajectory that has been verified by NMR. Let's examine how propene and propane traverse along the hexagonal channels of iron MOF 74. Propene is the yellow colored molecule. It is most strongly absorbed due to pi interactions with the unsaturated iron atoms that are located along the vertices of the hexagonal channels. Propene exerts a slowing down effect on the mobility of a propane, and this slowing down effect has important consequences for membrane constructs using iron MOF 74 for propene-propane separations. Cobalt BDP has square-shaped channels, and the alkane isomers such as normal pentane, 2-methylbutane, neopentane, normal hexane, 2-methyl pentane, 3-methylpentane, 2,2-dimethylbutane, and 2,3-dimethylbutane. These alkane isomers have different degrees of van der Waals interactions with the square walls, and cobalt BDP can be used to separate the alkane isomers based on the degree of branching. Hexane isomers can be separated using Fe2BDP3 that has triangular channels of 4.9 angstrom in size. The linear normal hexane molecules can locate along the vertices, affording improved van der Waals interactions. These channels are similar in shape to Toblerone chocolate. Within the triangular shaped channels of Fe2BDP3, 1,3,5-trichlorobenzene can be separated from its isomers 1,2,3-trichlorobenzene and 1,2,4-trichlorobenzene, because the 1,3,5 isomer can stack face to face within the triangular shaped channels. Let us examine the use of mordanite for separation of hexane isomers. Mordanite consists of 1D channels that are 7 angstrom in this direction and 6.5 angstrom in this direction. The 1D channels are connected to side pockets that have dimensions 4.8 and 3.4. The side pockets are unable to locate the hexane isomers. The hexane isomers are normally to be found along the straight 1D channels. And let's have a look at the animations for normal hexane conformations and 2,2-dimethylbutane. You will note that 2,2-dimethylbutane has a smaller footprint, and therefore at saturation it is possible to locate more of the 2,2-dimethylbutane within the 1D channels than normal hexane that has a longer footprint. In principle, it is possible, therefore, to separate the isomers of hexane exploiting on the entropy effects due to differences in the molecular footprints.